This is the third video of our Unit 6. It's on the law of conservation of energy. At the end of this video, you should be able to state the law of conservation of energy, calculate the total energy of given kinetic energy and potential energy, and use the law of conservation of energy to track changes in kinetic energy and potential energy. Let's get started. Here's a little bit of review from the first video. We said that when work is done, energy is changed. Energy isn't gained or lost, it's just changed. So what can happen to energy? Energy can be transferred from one object to another, or energy can be converted from one form to another. And we saw examples of that in the first video, and then in the second video, we saw the different forms of energy. The two main forms of mechanical energy are potential energy and kinetic energy. We said that potential energy is energy due to position, and this ball has potential energy that's gravitational potential energy due to its height off the ground. This ball on this side has kinetic energy, energy due to motion, and it only has kinetic energy when this man starts to push the ball. So what's happening is that potential energy, which is maximum at the height of the hill, is being converted into kinetic energy, the energy of motion, as the ball starts to move. The total amount of energy stays the same, but it's just transferred, converted from kinetic energy or from potential energy to kinetic energy. And that's the essence of the law of conservation of energy. So there are a couple of things that I want to say about the law of conservation of energy. And you can consider each of these things a part of the law of conservation of energy. First, energy cannot be created or destroyed. And this might sound familiar because we had the law of conservation of other things as well. In chemistry, you might have remembered the law of conservation of mass or the law of conservation of matter, saying that matter cannot be created or destroyed. We talked about the law of conservation of momentum, that momentum cannot be created or destroyed. And here we have the same kind of thing with energy. So what can happen with energy is that it can be transformed from one form to another, for example, from potential energy to kinetic energy, or from kinetic energy to potential energy, but it's not going to be created or destroyed. So the total amount of energy in a system doesn't change. It's going to remain equal. Let's look at what this means for a falling object. So here's a skateboarder that's just done a jump, and he's at the top of his jump right here, and then he's moving back towards a ramp. So he's falling through the air. Now, what I want you to bring to mind is our formulas for potential energy and kinetic energy. Remember, potential energy equals the mass in kilograms times little g, 10 meters per second squared, times the height in meters. Kinetic energy is 1/2 times the mass in kilograms times velocity squared. Now what happens is at the height of his jump, this skateboarder has maximum potential energy, and as he falls, he loses potential energy. And this is because his height decreases. And you could tell by this formula if you plug in different numbers. If height decreases, potential energy decreases, because height and potential energy are directly proportional. Now when he's falling, when he's at the peak here, he's not going to be moving at all. He'll be absolutely still in air for just a brief moment, and then he'll begin to fall because gravity's pulling on him. As he falls, he's going to be gaining kinetic energy because his velocity is increasing. And you can see from the formula that velocity and kinetic energy are directly proportional. But what you can see if you look at these numbers is the total energy never changes. Kinetic energy plus potential energy. At the top of the jump, his potential energy is 3,000 joules with a kinetic energy of 0 joules. Then, as he falls, he loses height. So his potential energy goes from 3,000 to 2,000, but the kinetic energy goes from 0 to 1,000. As he falls more, he gains more velocity, and his kinetic energy goes up and up until finally he's at the level of the ground He has no height, and the potential energy is 0. Let's look at another case. Here's another case of a pendulum. Now remember, a pendulum is something that you might see with like a hypnotist, where it swings back and forth and back and forth. Now how this conservation of energy or transformation of energy happens with a pendulum is when the pendulum, if we consider this kind of the ground level, when the pendulum is at its maximum height, that's when its potential energy is going to be maximum. So in this case, the potential energy is maximum at position 1 and at position 5. Kinetic energy of the pendulum is going to be max when the velocity is maximum, and that would be the case of position 3. Another way you can look at it is kinetic energy probably will be maximized in the examples that we see when the height is the least. As we study physics some more, we're going to see that things aren't always as easy as they seem at first. So I want to take this time to introduce another type of energy, and that's thermal energy. And you might know that word thermal to mean heat, and that's exactly what it is. Thermal energy is the energy that results in an object's temperature. So anytime an object has some temperature, it's going to have some thermal energy. And you can see an increase in thermal energy whenever there's friction, like when you rub your hands together, like this, just rubbing it back and forth. You could do that right now and feel the heat. This guy's doing it and really making physics look cool. Another way to see an increase in thermal energy is with a collision. And it doesn't have to be just a collision like a car collision. It can also be a collision just between anything. So here's a case where there are two metal balls, and those two metal balls collide and produce heat. Remind me after the video, and we'll check this out for real. So the two examples that we saw involved a pendulum or a ball kind of moving through the air, and the other case was a skateboarder moving through air. But if you look at something rolling on the ground, now we'd have to bring into consideration some thermal energy. First, let's use this as an opportunity to practice our potential energy and kinetic energy concepts. So in this case, we see maximum potential energy when the height is the highest. So, where's the maximum potential energy? That's going to be at point A. The minimum potential energy is going to be where the height is lowest. And in this case, that's going to be point D. Now the amount of kinetic energy is going to be inversely proportional to the amount of potential energy. So what you'll see is these two just flipped. So the kinetic energy is going to be maximum at point D, and the minimum is going to be at point A. But in all cases, total energy is going to be conserved. Kinetic energy plus potential energy, and in this case, since the ball is rolling against the ground and there's friction, we'd have thermal energy too. So think about it. Think about when there'd be the highest temperature of the ball. Let's explore that for a second. So when does friction come into play here when this ball is rolling? Anytime the ball is touching the ground. So when is there going to be maximum thermal energy? What do you think? D? A? Somewhere in the middle? It's going to be at point G, because at this point, the ball has come into contact with the ground for the longest. So there will be maximum thermal energy at point G, and minimal thermal energy before the ball starts rolling at point A. So if you noticed, the height of point A at the start is higher than the height of point G at the end. And if you tried to roll this ball up to the same height of point A over on the other side, it wouldn't work. And the reason is because when the kinetic energy is being transferred to potential energy on the way back up, some of that energy has been lost to thermal energy all along the way. So what would happen? The ball would stop at point G and it wouldn't be able to get all the way back up to point A because it wouldn't be able to get enough potential energy. Now I want you to be able to relate this back to what we did with our PhET ramp lab. And what we studied was a case with friction and a case without friction. And the case with friction looked like this. There was a 25-degree angle of a ramp. And this case is the file cabinet, and we started with it somewhere way up here at the top of the ramp. And what you'll notice is all of these different energy levels. The total energy level in orange, the thermal energy level in red, the potential energy level in blue, and the kinetic energy level in green. Now here's the start of the run, when the file cabinet was at the top of the ramp, and it was still. It had the maximum potential energy, shown here, and the minimum thermal and kinetic energy, shown down here. As the file cabinet slid down the ramp, what happened is friction caused thermal energy to rapidly increase. And as the file cabinet gained speed, it also increased its potential, or increased its kinetic energy. During all of that time, since we had an increase in thermal energy and an increase in kinetic energy, the amount of potential energy was decreasing. Once the file cabinet hit the bottom of the ramp, it was at its maximum speed, or maximum kinetic energy, and then it began to lose kinetic energy again, as friction acted against the motion of the file cabinet. As soon as the file cabinet hit the bottom of the ramp, you can also see that the potential energy was 0. So this PhET ramp lab was pretty complex. And without even knowing it, you learned the law of conservation of energy.